In many situations, we know the value of the equilibrium constant and the initial amounts of each of the species. Well, then we must solve for the equilibrium amounts. So far, we've had an easy time doing that, but now we get to some challenging problems. So we're going to take sample exercise 15.11 right here. We'll work through it step by step, and we'll let the book do some of the math for us, but I'll talk you through some of the more challenging pieces as well. So first we have a 1 liter flask filled with 1 mole of hydrogen, 2 moles of iodine at 448. The value of the equilibrium constant is 50.5. What are the equilibrium concentrations of H2, I2, and HI? So they want to know the E. So step number 1, skip a little space right here, write down the reaction, H2 plus I2, then goes to HI. Notice how I spaced it out. I left lots of room on all sides, especially over here. And then there's a 2 right here for HI. Over here, I'm going to have my initial skip a line, change, skip a line, end right here, ice table that for initial change equilibrium. And then notice they tell us what it's filled with initially. So initially we have 1 mole divided by 1 liter, so we have 1 molar of the H2. We have 2 moles divided by 1 liter, so we have 2 molar H2. I'm not doing sig figs on here right now, but you can see that there's lots of sig figs in those numbers. And then over here for HI, they don't talk about it at all, so remember we have to assume that there's 0 to start with. And then the other piece that we're given is the K sub C for the reaction, so K is equal to 50.5. So we know what products divided by reactants to the power of the coefficients will equal at equilibrium. Now we're not given any other information. In past problems we're told like the equilibrium concentration of one of these things and then we can figure them out. But here we're not told any of those. Since we're not told any of those, we have to resort to doing something we do in math. And the thing we do in math when we don't know something is we say, hey, there is an X amount or a variable amount. And so when the change takes place right here, we're going to lose X amount of this. And since there is a 1 in front of the H and a 1 in front of the I2, we will also lose X amount of this. So those are the same. But then over here at the HI, we will gain twice as much because there's a 2 in front of here. And so we will gain 2X. So lose X, gain X right here. And then we can add those together to get our equilibrium concentrations. So here we'll have 1 minus X, we'll have 2 minus X, and we'll have 0 plus 2X or 2X right here. Alright, so now since we've got it all in terms of the variable X, we can take and put it into the K equation, which of course is equal to 50.5, and that equals products. So HI, remember, to the second power, because there's a 2 right here, divided by reactants, H2 to the first power, times I2 to the first power, because there's a 1 there and a 1 there, so they'd be their first power, and remember they're multiplied together. And then we can take these variables, or these small equations, is what they are, and put them in for each place. So HI would end up being 2X, don't forget the whole thing is squared, and then I2 would be 2 minus X, and H2 would be 1 minus X. And you can remember back to your algebra days, when you have two quantities like this, you have to do first times outer times inner times the lasts. So you have to FOIL this animal to be able to solve that. And so you end up with 4x squared on the top, because remember the 2 is going to square here and the x is going to square here. And then after you FOIL this animal, you end up with these guys multiplying together to give you x squared minus 3x plus 2. And this is equal to 50.5, and you math people are jumping up and down right now because you recognize that this is going to end up being an equation that's got a square in it and a first power in it and a term that's a b term right here just with no x after it. And yes, you end up using the quadratic equation to solve this thing. And so when we take this and bring this to the other side and do some algebra to solve it, I'll do a little bit of it, but I won't do the whole thing. We end up with the 4 x squared, let's keep that on this side, and then let's multiply this side of the reaction by this part right here, is equal to the 50.5 times the x squared minus 3x plus 2. We've got to distribute this in here. And then we want to eventually set it equal to 0, because if we get the whole thing set equal to 0, then you can use your calculator to solve what's called the quadratic equation. Yep. And so I can go ahead and do a little bit of this. 50.5 x squared minus 151.5x plus 101, and then we'd subtract 4x squared from both sides to get this equal to 0, and then this would turn into 46.5 x squared, I think, and then minus 151.5x plus 101, and that's equal to 0. And now we have our negative b plus or minus 4ac plus or minus b squared minus 4ac all over 2a, and this is our a animal down here. And rather than me writing it all out, here it is in all its glory, the quadratic equation in your textbook. Now, hopefully you have a quadratic formula solver in your calculator, but 99% of the time they'll hopefully be ones where you don't have to do this. They'll be solvable without using the quadratic equation, but you do need to see one. And remember, the quadratic equation always ends up with two answers, so 2.32 is one of the answers, or 0.935 is the other answer. And if you take the x then that you solved for and put it back into these equations right here, if one of them ends up giving you a negative concentration, then that's your extraneous solution. That's the one that it can't be. 1 minus 2.32 would give you a negative concentration, and of course you could not have a negative concentration, so that can't be the answer. So our answer for x is 0.935. Remember, that's just x. We want to know the concentrations. So the concentration of H2 at the end would be 1 minus 0.935, which is 0.065 molar. The concentration for I2 at the end would be 2 minus 0.935, or 1.065 molar. And then the concentration of HI at the end would be equal to 2 times 0.935, which is 1.87 molar. All right, so remember, in these types of problems, you're going to end up knowing the initial concentrations, usually making an assumption there's none of this. You'll know the equilibrium constant, but you won't know any of the changes or any of the final values, and so you have to use x to determine that amount. Sometimes it results using the quadratic equation. Sometimes it results in just an equation where you can take the square root of both sides, and then it works out really nice. But that is an example of calculating the equilibrium concentration from initial concentrations.